Hey there, Calc 3 folks, back here with another lecture in our study of multiple integration, where this time around I want to introduce you to the idea of double integrals over polar regions. If you recall from Calculus 2, we introduced ourselves to the polar coordinate system, right? Where when we think about a location in two-dimensional space, not only could that location be described by an xy coordinate in what we understand as the rectangular coordinate system, a system that we've been familiar with since our early days of two-variable algebra, right? We also can describe that location, though, using what we call a polar coordinate, a coordinate in this form, r comma theta, right? Where theta, right, is an angle measurement that forms between the positive x-axis and some radial arm passing through the origin, right? And r describes some distance along that radial arm, right, described by theta, right, from the origin in the system, right? And in that relationship between x and y, we did happen to see in the polar coordinate system, its relationship back to the rectangular coordinate system. First of all, that's value of r, right? In our polar coordinate system, with respect to x and y, is always just the square root of x squared plus y squared. And even more so, what we could take note, and what I should have probably have noted here, is it can be the plus or minus of that radical, right? Theta is always the tangent inverse of our y coordinate over our x coordinate. In terms of how x and y relate to r and theta, x is always r times the cosine of theta, and in this relationship between x and r and theta, y is always r times the sine of theta. All right? Recall from Calculus 2, we established this understanding with respect to location in two-dimensional space, where we have this location described by in this polar coordinate system by this polar coordinate r comma theta, and the relationship of r comma theta back to those rectangular coordinates involving x and y, right? Well, what we're now going to consider having is the situation where we're going to perform a double integral calculation over this region R for function f with respect to the area of R, right? Where over this region R squared, right? That region R, right? Or I should say over this region R contained in R squared, this region R is this polar region of space. It is this region of space in two-dimensional space, right? It's this set of r comma theta coordinates in two-dimensional space, right? That describe our region of R, right? And in this particular case, we're going to have an approach for the calculation of the double integral over region R for our function f with respect to the area of R. And that's all presented here in the following theorem. Right? If I bring this theorem up into view, right? In the theorem, we are going to assume, right, here that we have this double integral of function f over region R with respect to the area of region R, right? For some function z equal to f of x comma y, that is now occurring over some polar region, where our polar region R, right, is described by this set of r comma theta coordinates in two-dimensional space. When we go to approach this double integral calculation, then, it is going to be calculated as a double integral over region R that now is going to occur with respect to r and theta, right? Where with respect to r and theta, it's going to first occur with respect to r and then occur with respect to theta, where we're going to perform this double integral calculation on an integrand for what is going to be function f described in terms of r and theta times some factor of r. How we're going to obtain function f in terms of r and theta is we do take note that the value of x in our multivariable function will be replaced with r cosine theta, and our value of y here in this multivariable function of f will be replaced with r sine theta. That function f in terms of r and theta then is multiplied by this, what we might think of as scaling factor of r, right? Where r, little r here, right, is the variable given by the radius, right? R. It is that distance from the origin, right? That is going to play the role of a variable in this calculation, very much so. Variable r and variable theta play a role of variables in this multivariable function. Now, in this setup, right, for the double integral calculation, right, region R is going to be occurring in a very specific manner, right? In this setup, in a double integral over a polar region, R is going to be described as follows, right? Again, it is the set of coordinates r comma theta contained in two-dimensional space, such that we put the following restrictions on that value, all right, or on those values, right? We restrict theta to be an angle measurement between alpha and beta, and we restrict little r, the distance from the origin along that radial arm formed by theta, all right? Dependent upon theta has to be stuck between these two functions of theta, g of theta and h of theta. If we think about the region over which this double integral calculation is occurring, that we're going to calculate in terms of the polar context here, it might be illustrated as follows. If I bring our description of r up into picture, all right? This is the quickest illustration I could put together for you, folks. I could be a little bit more generic in terms of my descriptions of g and theta, or g of theta and h of theta, but I think this will suffice. If I zoom in a little bit here on our description of r, can I get all of this in? Let me shrink that down just a little bit. Right here we can get both into the picture as one, right? We are talking about this set of points R, this region forming in our two-dimensional system. Here we can still see x and y axis exist in this two-dimensional system, and we could define all these coordinates in terms of x and y, but because of this describing a polar region, it's going to be better interpreted in the context of the polar coordinate system, where when we think about this description of r, it is going to be this set of coordinates r comma theta, describing all these locations within r, where we've put these restrictions on r and theta. First of all, theta are these angle measurements that, if we recall, form between a radial arm passing through the origin and the positive portion of the x-axis. We have this angle measurement here that forms, known as theta equal to alpha, right? And region R begins at that radial measurement in this picture and continues up through the radial measurement of theta, where theta is equal to beta. Beta being the angle measurement formed between this radial arm passing through the origin of our two-dimensional system and the positive x-axis here, right? Seen here in our illustration. R, this polar region, starts to form between this angle measurement of theta equal to alpha up to this region where theta equals beta. And it forms, right, between radial measurements from the origin between these polar functions of theta. The closest we are to the origin will be described by this function g of theta, right? This polar function g of theta. And the furthest any point will be in region R will be described by this polar function h of theta. G and theta and h of theta are describing the bounds on these coordinates where we're looking at a distance from the origin here. And we're looking at all the points whose distance from the origin are somewhere between g of theta and h of theta. These two polar functions that are described in terms of theta. Theta occurring between values of theta equal to alpha and theta equal to beta. Theta being the independent variable in these polar functions. All right? Now, if we look at an example, we'll pull up this example here. We might here consider this double integral calculation here. All right. This double integral calculation that occurs for, for this function f, this multivariable function f in terms of x and y given by 1 over x squared plus y squared, that occurs over this region R where we can see R has been defined in this polar context. Right? R has this description of theta happening between values of 0 and pi over 3, alpha equal to 0, beta equal to pi over 3, and little r, the radial distance, or I should say the radius distance from the origin, this measurement of distance along these radial arms from the origin, being stuck between these constant functions of theta, where g of theta is equal to the constant of 1 and h of theta is equal to the constant of 2. Right? If we interpret this interpretation in this particular case, right, for region R, we might note this region R is illustrated as follows. All right. This region R is again forming between angle measurement of theta equal to 0 up to an angle measurement of theta equal to pi over 3. Right? That's defining the region R, these angles between which it begins to form, these radial arms, or that this this region R begins to form between, where the distance we're going to be from the origin is going to be constant. It's going to be constantly between the value of 1 and 2 in value, where if we think about these constant functions in the polar coordinate system, they describe graphs that would actually be circles, right, in our system. The polar function g of theta equal to 1 is a circle centered at the origin with a radius of 1, and we are looking at that portion of the circle here from 0 to pi over 3. And region R forms between values where little r is then less than or equal to h of theta equal to 2, where h of theta equal to 2 describes a circle in this two-dimensional system here, right, that has a radius of 2 units. Right? Where we're interested in being the region R stuck between these two circles of radius 1 and radius 2 over these angle measurements of theta from theta equal to 0 to theta equal to pi over 3. Right? Now, what our theorem says in terms of the calculation of this double integral, as for the double integral calculation of this function, right, for function f of x comma y, if we go back and note, since x squared plus y squared will be equivalent to the value of r squared in the relationship between x and y and the value of r, right, we can then think of as function f, where we can find x squared plus y squared in the denominator, being expressed in terms of this multivariable function of r and theta, where that x squared plus y squared in the denominator here can be replaced with the value of simply r squared. All right? And this is how we would express this multivariable function f with respect to the coordinates found in the polar coordinate system. If we took that further then, and actually consider the double integral calculation, the double integral calculation, right, that's occurring for function f across region R with respect to a would be approached in this calculation here, right? Would be approached by the double integral calculation we see on the right-hand side, where if you recall, we are going to have to take the double integral of function f with respect to r and theta and multiply it by this factor of r, little r still being just the variable little r that we see in this multivariable function. And certainly we're going to see what happens there is a little nice cancellation, and that leaves us with an integrand of 1 over r. And this integration then has to occur in a very specific order. That order being dr d theta. Little dr, right? R occurring, an integral occurring across the bounds from 1 to 2, as we had seen defined, right? Back here in our description of R as these bounds between 1 and 2. And theta being the outer integral occurring across the bounds from 0 to pi over 3. The bounds we've saw expressed in terms of theta in our description of R in this polar coordinate system. All right. Simplifying our setup integration, right, what we were given by the theorem, we do have this integral calculation here, right? Where if we first integrate with respect to r, note what the antiderivative of 1 over r is with respect to r, right? That is a fundamental integration in terms of r, right? Keep in mind that gives us the ln of r. That's the one case we cannot use the power rule, folks. The antiderivative of 1 over r is the ln of r, which we're now just going to evaluate across the bounds from 1 to 2. Right? We can see that illustrated here. Where from 1 to 2, we would have the ln of 2 minus the ln of 1. We're just keep in mind the ln of 1 asks the question, e to what power gives us a result of 1? Well, e to the power of 0 gives us the result of 1. So the ln of 1 is actually equivalent to the value of 0. So the ln of 2 minus 0 is just the ln of 2, which is now just a constant value that we're going to integrate for values of theta from 0 to pi over 3. Integrating this constant with respect to the variable theta is just the ln of 2 times theta. All right? Again, another fundamental integration here, folks. This does just give us the result. The ln of 2 times theta, where that ln of 2 is a constant multiple, I can bring that outside of that antiderivative and evaluate that antiderivative from 0 to pi over 3. Evaluate theta from 0 to pi over 3 only. Now at 0, it's 0, but at pi over 3, it's pi over 3. So it's pi over 3 minus 0, which is pi over 3. And we're left with the pi over 3 times the ln of 2, or what we might say is ln of 2 pi over 3 units cubed as our value here. Right? Folks, the first example here, this double integral, right, of this multivariable function f over this polar region R is again going to yield a net volume calculation. That net volume given by the ln of 2 times pi over 3, or pi over 3 ln of 2, right? Units cubed. Where again in this calculation we are going to note have an integrand expressed by rewriting our function f in terms of r and theta. And the way that that is going to occur, folks, is we are going to have to go back and rely on this, or on these relationships between r, theta, x, and y, right? Here I relied on our very first relationship where r is equal to plus or minus the square root of x squared plus y squared. That does imply r squared equals x squared plus y squared. So using that fact, I was able to write f in terms of r and theta being 1 over r squared in the polar coordinate system. And what the theorem says is that we do have to multiply that value of f in terms of r and theta times some scaling factor of r. Now, this scaling factor of r that we are multiplying by, folks, it's going to become known as the Jacobian multiplier. All right? It does come about from what we call, or think of as change of variables. We are, in a sense, changing our variables from the xy interpretation that we're familiar with here in our initial double integral calculation in the rectangular coordinate system to a interpretation of variables in that space that happen in terms of r and theta. And when that occurs, right, there is this multiplying factor known as the Jacobian that occurs in the integrand, where the Jacobian is determined by, right, the relationship between the variables seen in the mapping of one dimension, in this case the one description of the two-dimensional space given by x and y, to a mapping of that dimensional space given by r and theta. All right? So that value of little r that we see is this multiplier in our theorem, and if I go back to the actual theorem and point this out, right? This is the value we're calculating down there in our calculation. We do want to find f in terms of r and theta and multiply it by this value of little r. That is your Jacobian multiplier when you think of transforming x and y's description of r into a description of r that happens in the polar coordinate system. It is a topic that we might hopefully have a chance to talk about here at the end of chapter 16 if I have enough time to get through all these videos. At least be able to get into maybe showing a little bit about where this value of r comes from in this Jacobian calculation, right? Or this interpretation of the double integral of r in the polar coordinate system. Other than that, folks, it is an integral that just happens where r and theta are now your variables, and you follow fundamental rules in that process. Or you could use substitution in the process, or maybe even some of those techniques that we went over in Calculus 2, some of those integration techniques. Here we use the integral rule, the antiderivative rule for 1 over r. That's the ln of r. And down here it was just in terms of the constant rule. All right? Some rather fundamental rules. All right? Let's consider another example. Let me bring this example into view. All right? Consider another double integral calculation here, where we might say we want to find the double integral over region R for function f with respect to the area of A, where function f is described by this multivariable function x divided by y. And R is the region within one petal of what we call the polar curve r equals sine 2 theta. Now, the polar curve r equals sine 2 theta is going to produce what is hopefully becoming a familiar looking polar curve. If you've studied your polar coordinate system back in Calculus 2, this was a polar curve that you may have encountered in your study known as a rose curve, right? Where this is going to be a 4-petal rose curve, and we're going to be interested in the double integral of f over a region of r that falls within just one petal of this 4-petal rose curve, right? Which is going to occur over values of theta, and I did help out a little bit here in denoting that these petals this one petal is going to occur over values of theta from 0 to pi over 2. Now, with that description of theta and this description of our curve, you could use your techniques from Calc 2 to describe that region of space and come up with a graphical description. I put this together on Mathematica, and what I might do is give you a quick little demo over how to get some of these descriptions of R in terms of using Mathematica here, and post that up. But here's the description of R we're talking about. This region of R that forms from angle measurement theta equal to 0, right? Theta equal to 0 falling along the x-axis around to where theta equals pi over 2, which would be straight up and down along the y-axis, the positive portion of the y-axis. As theta goes from 0 to pi over 2, this one loop of this 4-petal rose curve forms. Right? This rose curve found by the polar curve or polar function r equal to the sine of 2 theta. Right? If we think about interpreting then what region R would be described as in this case, we would see the following description for region R. Right? Note, in this particular case then, region R would be described as follows. Now, do I really have this error in here? Let me go in and fix this. This is the case where region R is this polar region, right? Described by the set of polar coordinates, where theta occurs from 0 to pi over 2. And R, this distance we are from the origin as theta cycles from 0 to pi over 2 in radial arms, right? From this radial arm up to this radial arm through all of these radial arms, right? R is going to be anywhere from 0 units away, right, up to what would be the sine of 2 theta units away. If I was to place a radial arm somewhere inside of region R, right, that distance that we would be at along that arm would be anywhere starting at the origin and going up to where the end of the rose petal would occur. Right? From 0 up to whatever would be the sine of 2 theta for that particular angle measurement of theta. Right? And this occurs for all values of theta from 0 to pi over 2. Now, certainly at 0, this is 0 in value, and at pi over 2, this is 0 in value, because we have returned to the origin on this rose curve. But for any other angle measurement between 0 and pi over 2, how far we will be away from the origin to help describe region R will be somewhere between 0 and the sine of 2 theta. So if we use that, along with information about our function f and our theorem for calculating double integrals over polar regions, we would have this calculation. All right? To begin with, recall for f, that was our polar function, or our rectangular multivariable function described by x over y. Well, here in our calculation, x over y, x is equal to r cosine theta, and y is equal to r sine theta. All right? What I might consider doing here, all right, let's add in another line here. Let me go copy equals, grab another one of these, and let's actually explicitly show that what we have here is that function of x and y occurring over region R, where we don't quite have a way of describing R in terms of x and y. Right? So what we do have to transform is this multivariable function in terms of x and y into a function of r and theta. And that is done by noting that x is always equal to r cosine theta, and y is always equal to r sine theta. Right? That is multiplied by this Jacobian factor inside our integrand. And we are going to have to integrate with respect to this very specific order of r dr d theta. R is going to occur across these bounds that we have in our description of R, right, laid out above. And theta is going to have to occur across these bounds seen in our description of theta above. Now, you are kidding me. I got to go back and replace all these. Okay, but I'll do that along the way here and fix your set of notes, right? So that's going to be from 0 to pi over 2. All right. Notice we do have some convenient canceling here. These two r's found in the numerator and denominator of x over y will cancel, leaving you just with the cosine theta, sine theta, and you could say that is also the cotangent of theta, but I will tell you it's going to be more convenient to leave it in this form for the moment, at least in this example. And that is still multiplied by this Jacobian factor of r, where I'm going to start my integration now with respect to r. And it's just this value of r that's going to be integrated. The cosine theta, sine theta, that cotangent of theta, is a constant multiplier. So if I just multiply, or I should say, find the integral of r, the antiderivative of r, that's going to be 1/2 r squared times this constant multiplier. All right? And we see that result in our next step. All right, where I'm going to quickly go through and fix my upper bounds here. That's what I get for copying and pasting. It's nice that I roll through these with you here so I can correct these along the way. All right. Make sure I get you as accurate a set of notes as I can. All right. So we were back here in this step. We just scrolled up to this step here. We are integrating with respect to r, right? R's antiderivative is 1/2 r squared. Now that 1/2 I do pull out as a constant multiple. I do have to leave the r squared on the inside, and I am going to evaluate that across these bounds from 0 to sine 2 theta. Now at 0, 0 squared is 0, and times this multiplying factor is constant factor here, right? Constant multiplier is still just 0. It zeroes away. But at the sine of 2 theta, it becomes the sine of 2 theta squared times this multiplying factor, right? This constant multiplier, cosine theta over sine theta. That cotangent of theta we had back here. All right? Now, to go further into this, to make this a little easier, I am going to grab a trig identity here, folks. I believe this is the double angle identity here for the sine of 2 theta. The sine of 2 theta in the double angle identity is 2 sine theta cosine theta. So this actually becomes the statement here in the integrand given by the 2 sine theta cosine theta quantity squared, where we are going to expand that out. When we expand that out, that becomes 4 sine squared theta cosine squared theta. And when multiplied by the cosine theta sine theta, you get some canceling of the cosine thetas and sine thetas found in the numerator and denominators of this product. As well as this 2 squared becomes 4, and that cancels with the 1/2 found out in front. That becomes 2. The sine squared theta cancels with the sine of theta in the denominator and becomes sine theta. And the cosine squared theta in the numerator, or found in this in this factor here for the cosine squared theta, gets multiplied by the cosine theta found in the numerator of this factor and becomes cosine cubed theta d theta. Where you'll note, how do we integrate this quantity? Well, here we go back to some chapter 8 techniques, or some of those Calc 2 techniques where we saw, what do we call this? We call this trig integrals, right? This is not trigonometric substitution. This is a little trig integrals, where we do note we have this sine of theta cosine theta, or times a cosine theta form, right? We have the product of a power of sine with a power of a cosine, right? And there is a suggested strategy for this. And if you recall that strategy says, first of all, pull out what you might call one factor of sine theta and convert the other even factors of sine theta into cosine of theta, put them in terms of cosine theta. Well, we don't have to worry about that here. We already have just our one factor of sine theta. Or now if we do a little u substitution, letting u equal the cosine theta, right, we can do a rather quick u substitution. Letting u equal the cosine theta does imply negative du would be equal to the sine theta d theta. Keep in mind the derivative of u with respect to theta for cosine theta is the opposite sine theta. So that produces this result, negative du is equal to the sine theta d theta. And if we go down here into our substitution, right, and we substitute in, right, for sine theta, negative du, that will turn into negative 2 du in our result here. If the u goes in for the cosine theta, that would become u cubed in our integrand. And then for our bounds, if I plug 0 in for cosine theta, that does become the value of 1. Whereas if I substitute in the upper bound here of pi over 2, which you've noticed I corrected, the cosine of pi over 2 is actually the value of 0. So I do have to correct this result here. All right? So with a little u substitution, I can turn this argument into this argument. Now you will notice these bounds are reversed, and we can go back to a fundamental rule of calculus that says if you have the order of your bounds, if you want to change those in an integral, you can do that by just simply switching the sign of the result. So instead of being minus here, we can, or a negative result, we can make this into a positive result by reordering our bounds. So you'll notice that's the first thing I do here. I do have to fix some of these bounds as I go along, right? So by switching the order of these bounds, now from 0 to 1, we can change that from negative 2 to positive 2, where I'm now just going to integrate u cubed with respect to u, which is a fundamental rule, folks, there. That's just your power rule, right? That's going to bump up to a power of 4, and we divide by 4th. That is 1/4 u to the 4th. Now, I guess I could have brought that out as a constant multiplier, but I did work it through across these bounds. Let me fix this. All right. Well, that certainly cleans up a lot nicer than what I had. Let's see here. At the value of 1, this does become 1/4, and at 0, it does 0 away. So we do have 2 times 1/4 minus 0, which is just 2 times 1/4, which in the end simplifies to the quantity 1/2 in value, right? So we have a value of 1/2 units cubed. Again, folks, what this is describing is what we think of as a net volume calculation. We are calculating the net volume trapped between this multivariable function f in terms of x and y equal to x divided by y over this region of R, where this region of R is conveniently, right, laid out in the polar context, laid out in a nice description that occurs in the polar coordinate system. You could imagine trying to describe this region here in the rectangular coordinate system, right? This does become a terribly more complicated description in the rectangular coordinate system, and the calculation of the double integral we're asked to calculate, which is a nice clean result. Notice that result, folks, of 1/2, right? This was found in a rather simplistic manner, nothing too terribly complicated. Whereas if I had laid out R's description, or attempted to, in the rectangular coordinate system, that certainly involving x and y would be a much more terribly complicated description here. In fact, it might even involve more than one region of R in its description, right? And the calculation of the actual integration that I have to perform along the way would most likely be a lot more complicated, because we would be trying to handle a polar description, right? Something that describes itself very conveniently in the polar coordinate system, in a rectangular context, which, if we go back to some of our Calc 2 understandings and what we're going to see here in the calculations for our calculations in the polar coordinate system just make things terribly complicated if we try it rectangularly. But in the polar context, sometimes become very simplistic in their calculations. All right. So, folks, that is my next video here in our study of double integrals. And actually, this does conclude our study of double integrals. We're going to continue looking at multiple integration, though, continuing on up into what we think of as triple integrals, folks. We are going to, your next video is going to focus in on some triple integral calculations in your study here. And their calculation and interpretation, which we'll note is very analogous to what we've developed and established up to this point. So if you haven't watched all the videos, make sure you go back and you watch those videos before we get into this study of multiple integration, right? But other than that, I guess hopefully you folks are all hanging in there. Again, hopefully you're checking in with me in those Blackboard Collaborate sessions. If you're having questions, I'm there many hours throughout the week, right? You can find me for an hour in the morning, afternoon, and in the evening, Monday through Thursday. So check out those schedules if you have any questions. I'm certainly happy to help, and I have a lot of ways of helping on there. But other than that, hang in there, folks, and I'll be back in the next video.